Hello, in this video we're going to talk about determinants. The first thing I'm going to do is I'm going to talk about what we're trying to achieve by defining determinants. Then we'll talk about its definition and then a few theorems. Okay, so what we're trying to achieve by defining determinants is defining areas of regions in 2-dimension or volumes of regions in 3-dimension or higher dimensions. So what kinds of regions are we talking about? Regions that are really related to linear algebra, which means there would be regions that are created by vectors. So in 2-dimension, let's look at a parallelogram created by two vectors, vectors u and v. I'm trying to define the determinant to give us the area of this region created by the vectors u and v. In 3-dimension, if I'm given 3 vectors, then I can define a region in 3-dimension called a parallelepiped, which is a 3-dimensional version of parallelograms, which would be a region that has 6 sides. The sides are pairwise parallel to each other. So the top side and the bottom side are parallel. The left and right are parallel, and the front and back are also parallel. So if you look at the vectors u, v, and w, we are trying to define determinant to give us the volume of this region. Now, in order to define determinant, we'll have to start from some properties that we expect the determinant to have, and then we will define it based on those properties. So we're going to create what we call like some axioms for the determinant, and then we're going to show that in fact there is such a function, and then we will show we will do some examples, and then we will show that in fact there's going to be a unique function satisfying these conditions that we're going to talk about, and that would be one of the main theorems of today. Okay, so let's look at some properties that this determinant must have. First of all, if you have a parallelogram where the two sides are the same, two adjacent sides are the same, it basically collapses to a segment, and we expect the volume, or in this case the area, to be 0. So any reasonable definition of volume would have to give us 0 if you're collapsing your region, your parallelepiped. This region in 3-dimension is called parallelepiped. So if you collapse your parallelepiped to 1 dimension less, you expect the volume to be 0. The second expectation that you have is a bit more complicated, but it's also natural. It is that if you fix your base, in this case the base is vector u. If you fix your base and you add two vectors v and w, you'll get this region. So this is the area of u and v plus w. Now you could break it down into two different regions. One is this one, which is volume of u, v, and one is this one. So if you look at this, we have essentially taken two parallelograms and put them together. Now the sum of these two parallelograms, uv and uw, is the same as the area of parallelogram based on u and v plus w. The reason is the two triangles in yellow, these two triangles have the same area. By SSS, you can see that they have the same, they are congruent and they have the same area. So one way of thinking about this is that when we add two vectors v and w, we are not changing the base, but we are increasing the height by the height when you add v and w. So in other words, the height here plus the height here is the height from here to here. So the height from the height for v and the height for w is going to be the height for v plus w, which is why the areas add up. Okay, so now if you look at the area of u comma cv, we get the larger area, this area, and that is c times the area of uv. And the reason is this height has been multiplied by c to get to this height, which is why, and the base is the same, which is why the area is also multiplied by a factor of c. So these three expectations are what we really have. So the first one, this one, well, I guess the second one, the one on the right, is what we call, if you think about this one, is a property that we have seen before. This property is called additivity. But in this additivity, u must be a fixed vector. So if you fix u, then you have additivity with respect to the second vector. This property also seems quite familiar. This is called homogeneity. And this one is not quite familiar, but we are gonna start calling this alternating. So the area of u comma u must be 0. Okay, so let's now formalize everything we talked about here. So let d from m and r to r be a function. We say d is multilinear. So what does multilinear mean? It means it is linear with respect to each of the rows. In other words, for every I, we have d of v1 all the way to, if you replace the ith row by avi plus bw, you can write it down as a d of, and then the ith row would be vi, and then once you do the ith row as w, and then you take out b. So that is linearity with respect to the ith row, and it should be linear with respect to every row. So that's called multilinearity, which is a property that we expect determinant to have. We say d is alternating if d of v1 through vn is 0 when two of those rows are the same. vi and vj are the same for some I not equal to j. At this point, we are formalizing this definition, but we haven't really related these two areas yet formally. But we will see that, in fact, there is an additional condition needed in order to relate this to area and in general volume. Okay, so let me now go ahead and look at one example. And also, to keep the notation more compact, instead of writing down d of v1 through vn vertically, I'll write it down as d of v1 comma v2 comma vn, inserting commas to indicate that v's are rows and not columns. Okay, so let's look at an example. The first property that we are basically forced to have, if we consider those two properties, is that when we swap two of the rows, d becomes negated. So in other words, we can't really define the area as something that is always positive. And that's one of the issues that arises. But in fact, it would be a nicer thing to have, because what happens is not only this tells us, this d would eventually tells us the area, but it would also tell us something about the order of these edges of the parallelepiped. So something, it replaces clockwise, counterclockwise, or right hand rule. So in general, that's actually an advantage, not a disadvantage. So let d from m to r be an alternating multilinear function. Prove that d of u comma v is equal to negative d of v comma u. So the trick for this one is we want to somehow relate d of u comma v and d of v comma u. I want to have u and v on the two rows of the matrix to be swapped. So what I'm going to do is I'm going to consider d of u plus v comma d of comma u plus v. I know this would be 0, and the reason is d is alternating. Now we're going to use multilinearity. So d of u plus v comma u plus v is going to be d of, so we'll use linearity with respect to the first one, u comma u plus v plus d of v comma u plus v. And so this is linearity with respect to the first component. Now we're going to use linearity with respect to the second component. So that would be d of u comma u plus d of u comma v plus d of v comma u plus d of v comma v, and again this follows from linearity. Now if you look at these two, this one and this one, these two are 0 by the fact that it is alternating. So this would be d of u comma v plus d of v comma u, and those two are 0 as we discussed right now. And this one we just showed that this is 0. So what does that mean? It means 0 equals d of u comma v plus d of v comma u, which would mean d of u comma v and d of v comma u are in fact negative of each other, which is exactly what we wanted to prove. So d of u comma v is equal to negative d of v comma u. And that is the end of the proof for this one. Now, really, if you think about this one, we didn't really use the fact that it's a 2 by 2 matrix. We only used the fact that it's alternating and multilinear. So we will see that this is in fact true for any n by n matrix. Okay, so here's the second example. I'll do this example to just give you an idea of what this function is going to look like. And then we will do some very important theorems. So the next one is find all alternating multilinear functions d from m to r to r satisfying d of I equals 1. Okay, so here is how we can find this alternating and multilinear function. So let's just start with assuming that d is alternating and multilinear. So assume d is one such function. So what I'm going to do is I'm going to use linearity, multilinearity and alternating and see what we get. So let's look at a matrix A. So let's say d of a11, a12, a21 and a22. This is d of, so let me just write down in the short form the horizontal form because that's just a little bit more convenient. So the first row is in terms of E1 and E2 is A11 E1 plus A12 E2. The second row is A21 E1 plus A22 E2. Now we are going to use multilinearity as we did before. So we will get 4 different terms. So we will get A11 d of, let me just do it in 2 steps. D of E1 comma A21 E1 plus A22 E2 plus A12 d of E2 comma A21 E1 plus A22 E2. So that's linearity with respect to the first one, the first row of the matrix. Let's do it again. We will get A11 A21 d of E1 comma E1 plus A11 A22 d of A1 comma E1 comma E2 plus A12 A21 d of E2 comma E1 plus A12 A22 d of E2 comma E2. Just to be clear, here we're using linearity. Here we are also using linearity with respect to different components, with respect to the first one and with respect to the second one. Now, if you look at d of E1 E1, because it's alternating, that would be 0. And this would also be 0 because it is alternating. So let's just drop those. So that just disappears. We get A11, A22, d of E1, E2. What is E1, E2? E1 is 1, 0 and E2 is 0, 1. Plus, okay, so d of E1, E2 and d of E2, E1 are negative of each other. That's the previous example. So here I'm using alternating and example, I believe 5.1. Yeah, the example above. So I'm going to replace this one by negative d of e1, e2. So that becomes negative. So I'm just going to replace d of e2, e1 by negative a12, a21, d of 1, 0, 0, 1. So I just swapped e1 and e2 and I got the identity matrix. Now d of identity is 1, so we get a11, a22 minus a12, a21. So this is what we did. We started with assuming that there is a function satisfying those properties, and we ended up getting that it is this function. So we got that d a11, a12, a21, a22 equals a11, a22 minus a12, a21 is the only function satisfying the assumptions if any such function exists. So note that we haven't proved that this function is one. We have shown if there is one, it would have to be this one. Now we will have to show that in fact this function is a function satisfying those properties. So now we will prove D does satisfy the given properties. So first, multilinearity. So let's start with multilinearity. If you look at D of A11, A12, A21, A22, that is given by A11, A22 minus A12, A21. Okay, so is this linear with respect to the first row? Yes. Why? Because you can write this down as a dot product. This is A11, comma, A12 dotted with A22, comma, negative A21. And by an example, D is linear with respect to the first row, because we know every dot product is linear. Now we could also write it down as a dot product using the second row. We can write it down as A21. The second row is A21, comma, A22 dotted with negative A12, comma, A11. So that means D is linear with respect to the second row. So what does that mean? It means D is in fact multilinear. So therefore D is multilinear. Okay, so it is multilinear. Now we will have to show it is alternating. So we just showed that it is multilinear, and now we're going to have to show it's alternating. So D of A11, A12, A11. So if two of the rows are the same, there's only two rows. This is equal to A11, A12 minus A12, A11, which is 0. And that means D is in fact alternating. Now let's look at D of the identity matrix. This would be 1 times 1 minus 0 times 0, which is 1. So therefore D does satisfy all of those conditions. So it is a function that satisfies those conditions, and it is the only function satisfying those conditions. Okay, so that is nice. Now let's move on to the next theorem, one of the first theorem in this chapter. So let D from Mn of R to R be alternating and multilinear, then it satisfies the following properties. The first one is swapping two rows negates D. Okay, so this one was just proved in the example that we saw. The only thing about this is that We proved it for 2 by 2 case, but the key to proving this one for n by n is very similar. So part A would be you look at d of v1 through. For the ith position, you replace it with vi plus vj, and for the jth position, you replace it with vi plus vj. I'm not going to repeat the same proof, but it's basically that. You replace this one. This is the ith position. This is the jth position. And then use multilinearity. Open this up. You get 4 terms. 2 of the terms are 0. The other 2 terms are the ones that swap ith and jth row. And that would give us the proof. Part B is scaling a row by C gives us scales D by C. So this follows from linearity. So this follows from multilinearity. Because multilinearity tells us that if you take D of V1 through and you do CVI and just let's do just 0 times 0, etc. Multilinearity tells us this all the way to Vn is equal to C D of V1 through Vn plus 0 times D of V1 through and then 0 Vn, but it's just 0 anyways. So that shows that it is in fact homogeneous, or if you scale one of the rows by C, D is going to be scaled by that same factor C. Adding a multiple of one row to a different row does not change D. So if you add one row, a multiple of one row to another row, so this is the ith position, it doesn't change D. So let's look at what that means. So if you look at D of V1, Vi plus CVJ all the way to Vn, this becomes, by linearity, this becomes D of V1, Vi, then Vn plus C D of V1, Vj, Vn. Now, this is the ith position. This is also the ith position. So it means this guy is 0 because 2 of the rows are the same. The ith row and the jth row in this second D are the same. So this becomes 0 because of alternating. So this becomes D of V1 through Vn, which is exactly what we wanted to prove. And this comes from the alternating. So we use linearity here, and then we're using alternating here. So this is multilinearity, linearity with respect to ith row, and then alternating tells you that one of those determinants, one of those D's is going to be 0. And just to be careful, this is not determinant yet. We haven't really defined determinant yet. Okay, so the last property is that if the rows V1 through Vn are linearly dependent, then D would be 0. Okay, so that's an interesting property. So let's assume that V1 through Vn are linearly dependent. So what does that mean? It means linear combination of some of them is one of them. So let's assume that perhaps the last row is a linear combination of the others. And it's very similar for the other ones that are, it's almost identical. So without loss of generality, assume Vn is C1 V1 all the way to Cn minus 1 Vn minus 1. So now we're going to evaluate D of V1 all the way to Vn. Simply we're going to use linearity. So this would be C1 D of V1 all the way to Vn minus 1 comma Vn, V1. So we are substituting the nth row by Vn, and we're going to use linearity with respect to the last row. So we get C1, and then the last one becomes V1. Plus, then C2 D of V1, v2 all the way to vn minus 1 and then v2 plus dot 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 all the way to cn minus 1 d of v1 vn minus 1 and also again vn minus 1. So as you see, this is by linearity, by multilinearity, linearity with respect to the last row. And as you see, each one of these is going to be 0 because two of the rows are the same. This one, the first row, and the last row are the same. This one, the second row and the last row are the same. This one, the last two rows are the same, so this whole thing becomes 0. And therefore, we got exactly what we wanted. Therefore, d of v1 through vn is 0 if v1 through vn are linearly dependent. It's very similar if one other row is in terms of is a linear combination of the other rows. Okay, let's go back and review this theorem. It's a very important theorem. We'll keep using that quite a bit. So let's review that. Swapping two rows negates d. Swapping two rows is exactly one of those row operations that we have seen before. Scaling a row by a factor of c multiplies d by c. That is also exactly one of the properties, one of the row operations that we have seen before. Adding a multiple of one row to a different row does not change d. That's also exactly one of the properties, one of the row operations that we have seen. Row addition or row replacement is exactly that. So as we see, each one of those properties is quite familiar. Each one of the first three properties corresponds to one of the row operations. We will talk more about this one later. Okay, so next we're going to talk about this very important theorem. This is an extremely important theorem. We'll talk about this, and I won't really be able to provide a complete proof. There is some portion of it that is a little bit more difficult than the rest, but I will be able to tell you the main ideas. For every positive integer n, there is a unique multilinear function d from mn of r to r satisfying this. Okay, first of all, we have done this theorem for n equals 2. If you go back and look at the example that I did earlier, we did this example of 5.2. Find all multilinear and alternating functions that satisfy d of I equals 1. Why do we assume that d of I equals 1? Because if you're trying to define volume, one thing that you can't do is you cannot just rely on those properties. Because, for example, d of everything equals 0 is also a function that satisfies all of those properties. It is multilinear and it is alternating. But you need to say some unit of measurement is also kind of fixed. So you need to say there is a cube whose unit, whose area, or whose volume is in fact 1. And here what we're going to do is we're going to say d of I, which is a unit cube, is 1. So if we assume that that's 1, then we're going to get exactly one way of defining the volume, and it would be a function satisfying these properties: multilinearity and alternating. Okay, so we're going to look at the sketch of proof. This wouldn't be a complete proof. Part of it needs some work. So if we look at, and the proof is going to be kind of similar to the example that we did, except it's in general case, so it's a little bit more difficult. So we're going to start with assuming that there is one, and we're going to show that there is a unique one. In other words, if there is one, it should be a certain form. So we're going to start with d of v1 through vn, and we're going to see how it would have to look like. We are going to look at the matrix, and we're going to write down all the rows in terms of e1 through en. So the first one would be d of e11 e1 all the way to a11 a1n en. That's the first row, all the way to an1 e1 ann en. Now, if I look at this one and use linearity, multilinearity, I will have to pull out these n terms from here, these n terms from the next one, and next one. So there are going to be n times n times n times, so there would be n to the power of n terms that we're going to get. So you would get the sum a1 something, so let's say a1 I1, a2 I2, all the way to an in d of ei1 all the way to ein. And what we know is that I1 through In are just elements of 1 through n. So you will run through every single possibility of I1, every single possibility of I2, every single possibility of I3, and so on. So you will have n to the power of n terms. Now, whenever I1 and I2 are the same, you will have a d that is completely zero. So anytime that two of these indices, I1 through In, are the same, d would be 0 because it is alternating. So what is left? What is left is the cases where I1 through In are distinct. What does that mean? It means they are a permutation. So this is equal to the sum a1 I1, a2 I2, all the way to an d of ei1 all the way to ein, and I1 through In is a permutation of 1 through n. Now, if it's a permutation, it means you can change this one to the identity matrix by swapping them. Keep swapping these EIs, and you get to the identity matrix. In other words, after you do that, if you do that, let's say once, and you get to identity matrix, you'll have a negative sign. If you do that, say 7 times, and you get to identity matrix, you'll also have a negative sign, because every time you're multiplying by negative. So negative 1 to the power of 7. But if you do that, say 10 times, then you'll get to identity, and you get to identity matrix, then you'll have to multiply by a negative sign 10 times. So in essence, this is going to end up being a1 I1, a2 I2, etc., an in, and there's going to be a plus or minus depending on how many times you need to turn this matrix right here into the identity matrix. In other words, if there is such a d, there can't be more than one. It would be just exactly this one. Another way of writing this one would be that it is equal to, you could, if you just write these as sigma of 1, and sigma is a permutation, sigma of n, this is typically the way we write it down, sigma from 1, it's a function from 1n to 1n, is a permutation. So there won't be more than one such function. Now we will have to actually define this function d and show that in fact it does satisfy those properties. Now the key part that is difficult, that is a little bit difficult to prove, is how do we determine this plus minus sign? How do we know which one to choose? And the answer is, of course, we have to see how many times we are swapping rows of this matrix right here to get to the identity matrix. But one might suspect that, okay, maybe you start from something, from a permutation, and you are able to get to identity in one way by swapping, let's say, 7 different rows. In other words, doing this swapping 7 times. Therefore, you have to define d of that negative one. But maybe somebody else comes up with a different way of getting to identity matrix using, say, 8 times. Then you'll have to define d of that positive one. And in that case, you can't really define such a function. There would be a contradictory, there would be like a contradiction here. So what we really need to prove is that this thing cannot happen. And that's the part that I'm going to skip. So this is basically a theorem. This is from abstract algebra. It can be proved at this level, but I'm going to skip that because it's really not really related to our discussion. So theorem is this. A permutation sigma 1 all the way to sigma n of 1 through n So let's put it this way. If a permutation this can be turned into 1 through n by L swaps and also by M swaps, then L plus M is even. Either both of them are even or both of them are odd, which means you cannot do it by, like, say 7 times and also by 8 times. Now, so the definition would be the sign of this permutation. Sign of this permutation is defined as negative 1 to the power of L, where L is the number of swaps needed to turn sigma 1 all the way to sigma n to 1 through n. If you need an even number of swaps, then it would be plus 1. If it's an odd number of swaps, then it would be minus 1. Now we can define D. D of A11, A1n, AN1, ANN can be defined as the sum of sine of sigma A1 sigma 1 all the way to AN sigma n, and then sigma is a permutation of 1 through n. So this is in fact the formula for determinant. Now it will have to be shown that it is in fact multilinear, it is alternating, and if you plug in identity you get 1. Those parts are not particularly difficult but quite time consuming. It's like a lot of write up. I will tell you why it is multilinear. The reason it's multilinear is that with respect to the first row, every term would have exactly one entry of the first row, which means you could think about this as the dot product of the first row and some vector. And same for the second row and so on. And then alternating is also not particularly difficult, but it is a bit more complicated. And identity gives you it gives you 1 is pretty straightforward. So I'm going to skip those. Now this function is called determinant. So finally we were able to actually define this determinant. Let D be the function in the above theorem. Then the determinant of an n by n matrix A whose rows are v1 through vn is defined as D of v1 through vn and is denoted by determinant of A. So let's use that those properties of D and evaluate this determinant. So we would like to evaluate the determinant of 1, 2, negative 1, 2, 0, 1, 3, 2, 1. Okay, we are going to employ those row operations to turn this into the identity matrix. So this is going to be equal to, we're going to make these two 0 by applying row 2 minus 2 row 1, row 3 minus 3 row 1. 1, 2, negative 1. This would be 0, minus 2 times that, plus that, that's 0, minus 4, 3 here, minus 3 times that, plus that, that's 0, minus 3, that gives you negative 6 plus 2, that's negative 4, that is 4. Now we are going to turn, we're going to turn this one into, okay, I'm going to actually pull out a 4 from the last row. So we're going to do 1/4 of row 3. So we're going to do 4 determinants. When you pull that out, you get 4 times determinant of 1, 2, negative 1, 0, negative 4, 3, 0, negative 4, negative 0, negative 1, 1. Okay, so I'm going to use this negative 1 and make these 0. Make this one and this one 0. We could do that. I mean, there's like multiple ways of doing that, but that's just one way. So I'm going to do row 1 plus twice row 3 and then row 2 minus 4 times row 3. That is 4 times determinant of, so 1, 0, 0. So the first row you have to add twice the last row to that, so that gives you 0. Twice this gives you 1. Negative 4 times that gives you 0. Negative 4 times that gives you negative 1. Negative 1, 1. Okay, we're gonna make this one and this one 0, and then we also need to swap at the end. So row 1 plus row 2, row 3 plus row 2, 4 times determinant of, so I'm adding row 2 to row 1, that gives you 1, 0, 0, 0, 0, negative 1, 0, negative 1, 0. Now we're going to swap, so row 2 and row 3 are going to be swapped for determinant of 1, 0, 0, 0, negative 1, 0, 0, 0, negative 1, and then we're going to take out negative 1 from row 2 and from row 3. We get 4 determinant of identity, which is 4. So determinant of this matrix would be 4, and this is typically the fastest way of evaluating determinant, at least at this point. So next time we'll talk about more properties of the determinant. So I will see you in the next video.